April 11, 1945, Nordhausen, Germany. Major James Hamel of the United States Army's Ordnance Technical Intelligence Team stands at the entrance to a tunnel complex carved into the Kohnstein Mountain in the Harz region, and even from the entrance he can smell death, the acrid stench of human waste, decay, and suffering that permeates the underground factory complex that German forces have just abandoned as American troops advance. Hamel has been tasked with locating and securing German advanced weapons before Soviet forces arriving from the east can capture them, and intelligence reports suggest that this facility, known as Mittelwerk, has been producing the V-2 rocket, the ballistic missile that has been falling on London and Antwerp for months, and which represents a quantum leap in military technology that American and British scientists have been desperate to understand and counter. As Hamel and his team enter the tunnels with flashlights, cutting through the darkness and illuminating the massive underground chambers, they discover an industrial facility of staggering scale. 46 interconnected tunnels, each approximately 2 kilometers long, equipped with railway tracks, machinery, assembly fixtures, and the infrastructure needed to mass-produce the world's most advanced weapon system in conditions of complete concealment from Allied bombing. The tunnels are littered with partially assembled V-2 components, technical documents, tools, and the detritus of hasty evacuation. But what shocks Hamel more than the technical sophistication is the evidence of the human cost. The prisoners' barracks built into side chambers where workers were confined between shifts, the primitive sanitation that explains the overwhelming stench, the evidence of malnutrition and disease, and most horrifyingly, the bodies of prisoners who died in the final days before liberation, and whose corpses the Germans apparently didn't bother to remove before fleeing. What Hamel doesn't yet understand as he catalogs the V-2 components and technical documents for shipment to American facilities is that the rocket technology he's recovering represents not just a military weapon, but the foundation for the entire space age that will follow, and that the scientists who developed this technology, many of whom are at this moment attempting to evade Soviet capture and make contact with American forces, will within months be brought to the United States under a program that will deliberately conceal their involvement in war crimes and present them as valuable assets whose expertise justifies overlooking their Nazi past. The V-2 rocket that Hamel is examining in pieces scattered through these death-scented tunnels is simultaneously one of humanity's most impressive technical achievements and one of its most morally compromised, built by slave labor under conditions so brutal that more people died building V-2s than were killed by the weapons themselves. And the American decision to embrace the scientists responsible for this horror will create moral contradictions that persist to this day. The story of how American engineers examined captured V-2 rockets and realize that German rocket technology is a decade ahead of anything the United States or Britain has achieved, begins not in the tunnels at Nordhausen, but on a Baltic island called Usedom, where in the 1930s, a young engineer named Wernher von Braun convinces the German military to fund research into liquid-fueled rockets as potential weapons. Von Braun is 25 years old in 1937 when the German army establishes a secret research facility at Peenemünde on Usedom, and he becomes technical director of a program that will eventually employ thousands of scientists, engineers, and technicians in pursuit of a weapon that most military officers consider science fiction, a rocket capable of carrying a 1-ton warhead across hundreds of kilometers, climbing to the edge of space and descending at supersonic speeds that make interception impossible with contemporary air defense technology. The technical challenges that von Braun and his team face at Peenemünde are staggering because nobody in the world has successfully built a large liquid-fueled rocket that can operate reliably. And every aspect of the V-2's design requires solving problems that have never been solved before. The rocket must generate thrust sufficient to lift its own weight plus fuel plus payload to altitudes exceeding 80 kilometers, which requires an engine producing approximately 25 tons of thrust, far more than any rocket engine that has ever been built. The engine must burn liquid oxygen and alcohol at rates exceeding 100 kilograms per second, which requires turbopumps spinning at thousands of revolutions per minute to force propellants into the combustion chamber at pressures high enough to sustain efficient combustion, and these turbopumps must operate reliably under conditions where failure means explosive destruction of the rocket and potentially death of anyone nearby. Von Braun's team develops the turbopump through years of trial and error that includes numerous catastrophic failures, explosions, and setbacks that would discourage less determined engineers. But von Braun possesses a combination of technical brilliance and obsessive determination that drives the program forward despite failures that destroy prototypes, kill test personnel, and consume resources at rates that military administrators consider wasteful. The turbopump that eventually emerges from this development process is a masterpiece of mechanical engineering. A device that spins at 5,000 revolutions per minute while pumping cryogenic liquid oxygen and alcohol at flow rates that would destroy conventional pumps within seconds. And the pump achieves this through innovations in bearing design, seal technology, and material selection that represent genuine advances in rotating machinery. Engineering that will influence turbopump design for decades. The combustion chamber and nozzle assembly that converts chemical energy in the propellants into kinetic energy in the exhaust gases presents equally daunting challenges because the combustion process generates temperatures exceeding 3,000 degrees Celsius, hot enough to melt any known material, and the chamber walls must survive these temperatures for the 65 seconds that the engine burns during powered flight. Von Braun's engineers solve this problem through regenerative cooling, where alcohol fuel is pumped through passages in the combustion chamber walls before entering the combustion chamber, and the alcohol absorbs heat from the walls while being preheated for more efficient combustion, creating an elegant solution where the fuel serves dual purposes as both coolant and propellant. The implementation requires manufacturing a double-walled combustion chamber with intricate internal passages that distribute cooling flow evenly and prevent hot spots that could cause wall failure. And the manufacturing techniques that German engineers developed to produce these chambers represent significant advances in precision metalworking and welding of high-strength alloys. The guidance and control system that keeps the V-2 on course during powered flight represents another domain where von Braun's team must pioneer entirely new technologies, because the rocket climbs so fast, reaching speeds exceeding 5,000 kilometers per hour, that conventional aerodynamic control surfaces become ineffective, and the rocket must be stabilized and steered through other means. The solution involves gyroscopes that sense the rocket's orientation in 3 dimensions, an analog computer that calculates required thrust vector changes based on gyroscope inputs and program trajectory parameters, and a system of graphite vanes mounted in the rocket exhaust that deflect the exhaust stream to generate control forces that steer the rocket. The graphite vanes must survive immersion in the 3,000-degree exhaust stream while providing control authority sufficient to correct the rocket's trajectory, and the vanes accomplish this through material selection, graphite that ablates slowly in the exhaust, and through design that balances control effectiveness against structural survival. The supersonic aerodynamics of the V-2's flight profile present challenges that push the boundaries of contemporary aerodynamic knowledge because the rocket accelerates through the speed of sound during powered flight and then continues accelerating to approximately 5 times the speed of sound before engine cutoff. And during this flight regime, the rocket experiences aerodynamic forces and heating that no aircraft of the era encounters. Von Braun's aerodynamicists developed the V-2's distinctive shape through wind tunnel testing and theoretical analysis, creating a design with a sharply pointed nose to minimize drag at supersonic speeds, a cylindrical body that houses fuel tanks and equipment, and 4 large tail fins that provide stability during the early phases of flight when speeds are lower and aerodynamic forces are still significant. The fins are carefully sized and positioned based on calculations and testing that explore how supersonic airflow behaves around bodies of revolution. And while the theoretical understanding of supersonic aerodynamics in the early 1940s is primitive, compared to modern knowledge, von Braun's team develops empirical understanding through testing that allows them to create a workable design. Adolf Hitler initially shows little interest in the V-2 program because he considers rockets to be expensive toys with limited military value compared to conventional artillery and aircraft. And Peenemünde operates through the late 1930s and early war years with modest budgets and limited priority for resources. This changes dramatically in 1943 when Hitler becomes convinced that wonder weapons, including the V-2, might reverse Germany's deteriorating strategic situation, and he orders the program to receive top priority with unlimited resources allocated to achieving operational deployment as rapidly as possible. This sudden elevation from low-priority research program to highest priority weapons program creates enormous pressure on von Braun and his team to accelerate development and begin mass production before the weapon is fully mature, and the premature push to production will create reliability problems that plague V-2 operations throughout its combat use. The British Royal Air Force becomes aware of German rocket development through intelligence reports and photographic reconnaissance of Peenemünde. And in August 1943, the RAF conducts a massive bombing raid using nearly 600 heavy bombers that devastates the research facility, kills hundreds of personnel, including key scientists and engineers, and forces the Germans to disperse V-2 production to underground facilities that will be less vulnerable to bombing. This decision to move production underground leads directly to the construction of the Mittelwerk facility in the Kohnstein mountain and to the decision to use concentration camp prisoners as labor for building the facility and manufacturing the rockets. And this is where the V-2 program crosses the line from military weapons development into direct participation in the Holocaust's machinery of death. The Dora-Mittelbau concentration camp is established specifically to provide slave labor for V-2 production, and conditions in the camp are among the worst in the entire concentration camp system, because prisoners are worked literally to death under the theory that their labor value exceeds the cost of feeding them minimally, and that replacements can be continuously supplied from other camps. prisoners excavate the tunnels using hand tools and explosives while breathing rock dust and working shifts that last 12 hours or more with inadequate food, no medical care, and savage punishments for any perceived failure to work fast enough. Thousands of prisoners die from malnutrition, disease, industrial accidents, and outright murder by SS guards and capos who run the camp with deliberate brutality designed to extract maximum work before prisoners collapse and die. And conservative estimates suggest that at least 20,000 prisoners died at dora-mittelbau between 1943 and 1945, more than twice the number of people killed by V-2 strikes on London and Antwerp. Wernher von Braun visits dora-mittelbau multiple times to inspect V-2 production and resolve technical problems with manufacturing, and he observes the conditions under which prisoners work and the brutal treatment they receive from guards. And while von Braun will later claim that he was merely a scientist focused on technical work and had no direct responsibility for how labor was sourced or managed, documentary evidence and survivor testimony make clear that von Braun knew prisoners were being worked to death and that he personally selected skilled prisoners from the camp population to work on specialized tasks, which means he actively participated in the slave labor system even if he didn't personally beat or kill prisoners. Von Braun joins the SS in 1940 with the rank of Sturmbannführer, equivalent to major. And while he will later characterize this as a formality necessary to continue his rocket work, the SS membership demonstrates his willingness to formally affiliate with the organization responsible for implementing the Holocaust. And this affiliation will become deeply problematic when the United States decides to bring him to America after the war. The first operational V-2 is launched against Paris on September 6, 1944, and over the following 7 months, approximately 3,000 V-2s are launched against Allied cities, with London and Antwerp being the primary targets. And the rockets kill approximately 5,000 civilians and cause significant psychological terror, because they arrive without warning. Unlike the V-1 flying bomb, whose engine noise provides some warning before impact, the V-2 travels faster than sound, and the explosion is the first indication that a rocket has arrived. The military effectiveness of the V-2 is questionable because the guidance system's accuracy is poor, with average missed distances measured in kilometers, making the weapon useless against military targets and relegating it to terror bombing of cities where precision isn't required. The economic cost of the V-2 program is staggering, with each rocket costing approximately 100,000 Reichsmarks to produce, equivalent to the cost of several fighter aircraft, and the resources invested in V-2 production, including the enormous quantities of alcohol fuel required, the slave labor that could have been used in other war production, and the industrial capacity consumed by rocket manufacturing, represent diversions from conventional weapons that might have been more militarily effective. As Germany collapses in early 1945, von Braun and his core team of several hundred engineers and scientists make a deliberate decision to surrender to American forces rather than Soviet forces, because they correctly assess that the Americans will value their expertise and will provide better treatment than the Soviets, who have suffered enormously from German aggression, and who are likely to treat captured German weapons scientists harshly. Von Braun organizes an evacuation from Peenemünde, taking key personnel and 14 tons of technical documents to Bavaria, where the team hides in a mountain village and waits for American troops to arrive. And on May 2, 1945, von Braun's brother Magnus makes contact with American forces and negotiates the surrender of the rocket team, presenting the Germans as valuable technical assets who can provide the United States with rocket technology that will be crucial in the emerging competition with the Soviet Union. The Americans who receive von Braun's surrender include intelligence officers who immediately recognize the potential value of German rocket expertise and begin arranging for the scientists to be brought to the United States. But this creates immediate problems because official American policy, as expressed in Joint Chiefs of Staff Directive JCS 1067, explicitly prohibits bringing Nazis to the United States and requires that German scientists with any connection to war crimes be prosecuted rather than employed. Von Braun and most of his key engineers are members of the Nazi Party and the SS. They have directly participated in war crimes through their involvement in the slave labor program at dora-mittelbau, and under a strict interpretation of American policy, they should be prosecuted as war criminals rather than brought to America as honored guests. The resolution to this contradiction comes through Operation Paperclip, a program initially established to bring German scientists to the United States for limited periods of interrogation, but which evolves into a systematic effort to permanently relocate valuable German technical personnel to America, while deliberately concealing or minimizing their Nazi affiliations and war crimes involvement. The name paperclip comes from the practice of attaching paperclips to the files of German scientists who have been cleared for recruitment, and the program operates through a combination of official channels and informal arrangements that bypass normal immigration and security procedures. The key mechanism that makes paperclip work is the willingness of intelligence officers and military administrators to falsify or sanitize the records of German scientists, removing references to Nazi Party membership, SS affiliation, and war crimes involvement, and creating cover stories that present the Germans as unpolitical technical experts who were forced to work for the Nazi regime, but who personally opposed its ideology and crimes. Von Braun's file is sanitized to remove references to his SS membership and to downplay his involvement in the dora-mittelbau slave labor program. And a narrative is constructed presenting him as a visionary scientist whose only interest was space exploration, and who was forced by circumstances to work on military rockets, but who never supported Nazi ideology and who had no direct involvement in atrocities. This narrative is factually false. Von Braun voluntarily joined the SS. He personally visited dora-mittelbau and selected skilled prisoners for work assignments, knowing they would likely die from the brutal conditions, and he enthusiastically supported the Nazi regime until Germany's defeat became inevitable. But the narrative serves the purpose of making von Braun acceptable to American authorities who want his expertise, but who cannot publicly embrace an unrepentant Nazi war criminal. The sanitization process includes coaching von Braun and other German scientists on how to answer questions about their Nazi past, instructing them to emphasize their scientific motivations while minimizing political involvement and ensuring that survivor testimony about their direct involvement in war crimes doesn't reach American prosecutors or journalists who might create public relations problems. In September 1945, von Braun and approximately 100 of his core team members arrive at Fort Bliss, Texas, where they're installed in a hastily arranged facility and begin working with American military personnel to share their rocket knowledge and to supervise the assembly and testing of V-2 rockets that have been shipped from Germany in pieces. The arrangement is awkward because the Germans are technically prisoners of war being held for interrogation, but they live in comfortable quarters, receive generous pay, and are treated as valued consultants rather than as war criminals or even as defeated enemies. American rocket engineers and scientists who begin working with von Braun's team are initially skeptical of German claims about V-2 capabilities because the performance specifications seem impossibly advanced compared to American rocket technology. But as the Germans explain the V-2's design and demonstrate captured hardware, American engineers are forced to confront the reality that German rocket technology is genuinely a decade ahead of American capabilities. The technical examination of captured V-2 components that American engineers conduct at facilities, including the Naval Research Laboratory, the Army's Aberdeen Proving Ground, and various university laboratories, reveals engineering sophistication that impresses and humbles American experts who have worked on American rocket programs and who thought they understood the state-of-the-art in rocket technology. The V-2's turbopump is disassembled and studied in minute detail, and American engineers who examine the device recognize that it represents solutions to problems that American turbopump designers are still struggling with. Problems like how to seal rotating shafts carrying cryogenic fluids without leakage, how to design bearings that can operate in liquid oxygen without lubrication that would contaminate the oxidizer, how to balance rotating assemblies, spinning at thousands of RPM to minimize vibration that could cause catastrophic bearing failure, and how to manufacture components with the precision necessary to maintain tight clearances under operating conditions. American engineers photograph every component, measure every dimension, analyze materials to determine composition and heat treatment, and attempt to understand not just how the turbopump works, but why German designers made specific choices about configuration, materials, and manufacturing processes. The combustion chamber and regenerative cooling system are examined with equal thoroughness, and American engineers who understand the theoretical principles of regenerative cooling are nonetheless impressed by the manufacturing sophistication required to produce the V-2's double-walled chamber with its intricate internal cooling passages. The welding techniques that join the inner and outer walls while creating leak-tight passages that can withstand both the internal pressure of the propellant flow and the thermal stresses of rapid heating and cooling represent welding expertise that American manufacturers don't routinely achieve. And American metallurgists analyze weld samples to understand what alloys German welders used, what welding processes they employed, and how they achieved consistent quality in welds that must be perfect, because any leak would cause catastrophic chamber failure. The chamber's throat region, where exhaust gases accelerate to supersonic speeds, receives particular attention, because this is where thermal stresses are most severe and where the cooling system must work most effectively. And American engineers note that German designers have optimized the cooling passage geometry in this region to provide maximum heat transfer exactly where it's needed most. The guidance and control system reveals sophistication in analog computing and electromechanical integration that surprises American engineers who have worked on guided missiles and who understand how difficult it is to create a system that can sense orientation, compute trajectory corrections, and command control responses quickly enough to stabilize a vehicle that's accelerating violently and experiencing rapidly changing aerodynamic forces. The gyroscopes that sense the V-2's attitude are precision instruments that must maintain stable spinning rotors while mounted in a vehicle experiencing intense vibration and acceleration, and American engineers who examine the gyroscopes note the high-quality bearings, the careful mass balancing of the rotors, and the sophisticated signal pickup mechanisms that translate gyro precession into electrical signals that can feed the analog computer. The analog computer itself is a mechanical marvel built from cams, gears, and electrical contacts that together implement the mathematical relationships necessary to transform gyro signals and program trajectory parameters into thrust vector commands, And while electronic computers are beginning to emerge in 1945, the V-2's mechanical computer represents the state-of-the-art in analog computation and demonstrates that mechanical systems can perform complex real-time calculations if designed with sufficient care and precision. The radio cutoff system that terminates powered flight when the rocket reaches the desired velocity is examined and reveals another domain where German engineers have achieved reliability in systems that must function perfectly in harsh environments, because failure means the rocket will either fall short of the target or overshoot, and either error degrades the weapon's already poor accuracy. The system uses a radio receiver in the rocket that picks up signals from a ground-based transmitter, and the receiver's electronics must survive the intense vibration and acceleration of launch, must continue operating as the rocket climbs away from the transmitter and signal strength decreases, and must reliably detect the cutoff command and trigger the engine shutdown mechanism at the precise instant when the rocket's velocity matches the required value for the desired range. American engineers who examine the radio cutoff system note the robust construction of the receiver, the careful shielding that protects electronics from electromagnetic interference generated by the rocket's own systems, and the redundancy in critical circuits that ensures the system will function even if individual components fail. The aerodynamic design of the V-2's airframe is analyzed through wind tunnel testing of captured components and through reconstruction of the German design process based on technical documents that were captured along with hardware. And American aerodynamicists who study the V-2's shape recognize that German engineers understood supersonic flow better than the Americans had assumed, and that the V-2's configuration represents thoughtful optimization for the specific flight profile of a ballistic missile that must minimize drag during powered ascent, maintain stability through the transonic regime where shock waves form and aerodynamic characteristics change dramatically, and survive the heating and structural loads of high-speed flight through the atmosphere. The sharply pointed nose that characterizes the V-2's appearance is not merely aesthetic, but represents the minimum drag configuration for supersonic flight, and the specific nose cone angle and shape are optimized through testing to achieve the best compromise between drag reduction and structural weight. The tail fins are sized and shaped based on stability calculations that ensure the rocket remains oriented correctly during powered flight when aerodynamic forces are significant, and the fin design includes adjustments to account for how stability changes as the rocket accelerates from rest to supersonic speeds and as propellant is consumed and the center of gravity shifts forward. American engineers who work on assembling and testing captured V-2 rockets at White Sands. Proving Ground in New Mexico gain hands-on experience with German manufacturing quality and learn to appreciate the attention to detail that characterizes V-2 production despite the horrific conditions under which the rockets were built. The rockets that are shipped from Germany in pieces and reassembled in America prove to be well made with components that fit together properly, with no evidence of shortcuts or poor workmanship that might have been expected given the use of untrained slave labor. And American engineers eventually learn that the Germans achieved this quality through brutal supervision, where prisoners who made mistakes were beaten or killed, and where fear of punishment motivated extreme care in work that prisoners would otherwise have had every reason to sabotage. The moral horror of this production system doesn't fully register with most American engineers who are focused on technical learning and who have been carefully insulated from knowledge about the slave labor system through the sanitization of German scientists' records and through official narratives that present the V-2 as a technical achievement divorced from the atrocities that made it possible. The test program at White Sands launches captured V-2 rockets to verify their performance, to train American personnel in handling and launching large rockets, and to gain operational experience that will inform American rocket development programs. The launches reveal both the capabilities and limitations of the V-2 design, with successful flights demonstrating that the rockets can indeed reach altitudes exceeding 100 kilometers and can carry scientific instruments into the upper atmosphere, where they collect data about atmospheric composition, cosmic radiation, and other phenomena that cannot be studied from ground level or from aircraft. But failed flights also demonstrate that the V-2's reliability is poor, with failure rates exceeding 30% due to turbopump failures, guidance system malfunctions, structural failures, and various other problems that weren't fully solved before the Germans were forced into premature operational deployment by Hitler's demand for wonder weapons. Von Braun's role in the American rocket program evolves from temporary consultant to permanent employee as the emerging Cold War competition with the Soviet Union creates demand for American missile capabilities that can counter Soviet threats, and by the late 1940s, von Braun and his team have moved from Fort Bliss to Redstone Arsenal in Huntsville, Alabama, where they work on developing improved rockets based on V-2 technology, but incorporating American innovations and addressing the reliability problems that plagued the German design. The Redstone rocket that emerges from this work in the 1950s is essentially an improved V-2 with better guidance, more reliable systems, and performance specifications that exceed the original German design. And Redstone becomes the basis for a family of American missiles, including the Jupiter Intermediate Range Ballistic Missile, and ultimately the Saturn II rocket that begins American heavy-lift rocket development that leads to the Saturn V and the Apollo Moon program. The parallel Soviet rocket program follows a remarkably similar trajectory, with Soviet forces capturing V-2 components and production facilities in their occupation zone of Germany, with Soviet intelligence agencies recruiting or forcibly relocating German rocket scientists to the Soviet Union, and with Soviet engineers studying captured V-2 technology and using it as the foundation for Soviet missile development. The Soviets are initially more ruthless than the Americans in exploiting German expertise, holding captured scientists in conditions approaching imprisonment and forcing them to work on Soviet rocket programs with the implicit threat that refusal will result in being sent to labor camps. But the Soviets also begin developing indigenous rocket expertise more aggressively than the Americans initially do. And by the late 1940s, Soviet engineers led by Sergei Korolev are designing rockets that build on V-2 technology but incorporate Soviet innovations, and that are specifically optimized for Soviet strategic requirements, including the need to deliver nuclear warheads across intercontinental distances. The R-1 missile that the Soviets develop as their first operational ballistic missile is essentially a copy of the V-2 built from Soviet components using Soviet manufacturing techniques, and the development process teaches Soviet engineers the same lessons about large rocket design that American engineers are learning from their V-2 work, including how to build reliable turbopumps, how to achieve stable combustion in large engines, how to design guidance systems that can operate under the harsh conditions of rocket flight, and how to manufacture complex systems with the precision necessary to achieve reliable performance. The experience with the R-1 allows Soviet engineers to design the R-7 rocket that becomes the world's first intercontinental ballistic missile in 1957, and that launches Sputnik later that same year, inaugurating the space age and demonstrating Soviet technological capabilities that shock the American public and government, and that trigger the space race that will dominate the 1960s and culminate in American astronauts landing on the moon in 1969. Von Braun's transformation from Nazi SS officer who oversaw slave labor production of V-2 rockets to celebrated American space hero who becomes the public face of NASA's moon program represents one of the most remarkable personal reinventions in modern history, and the transformation is carefully managed by von Braun himself and by American officials who recognize that von Braun's technical expertise is valuable enough to justify the moral compromises required to conceal his Nazi past from the American public. Von Braun becomes a naturalized American citizen in 1955, and he cultivates a public persona as an idealistic scientist whose lifelong dream has been space exploration and who views military rockets as merely necessary intermediate steps toward achieving his true goal of enabling human spaceflight. This narrative is not entirely false. Von Braun genuinely is passionate about space exploration, and he does envision rockets as enabling human expansion beyond Earth, but the narrative carefully elides his enthusiastic participation in the Nazi regime, his SS membership, his direct involvement in war crimes, and his willingness to use slave labor and to tolerate mass death in pursuit of his technical goals. The sanitized version of von Braun's history that is presented to the American public emphasizes his collaboration with Walt Disney on television programs that popularize space exploration, his charm and eloquence in explaining rocket science to non-technical audiences, his role in developing the Saturn V rocket that carries astronauts to the moon, and his vision of a future where humans live and work in space, and this version is enormously successful in creating public support for the space program and in positioning von Braun as a visionary leader whose technical genius and inspiring vision justify the enormous resources being invested in Apollo. The reality that von Braun built his expertise through work that killed thousands of concentration camp prisoners is known to journalists and historians who investigate his background. But during the 1950s and 1960s, this information is largely suppressed through a combination of government classification of embarrassing documents, reluctance by media to challenge the space program's heroic narrative, and von Braun's skillful deflection of questions about his Nazi past through carefully rehearsed responses that minimize his involvement and emphasize that he was merely a scientist working on rockets rather than a political actor involved in atrocities. The ethical reckoning with von Braun's past and with Operation Paperclip more broadly begins in the 1970s as classified documents start to be declassified, as survivors of dora-mittelbau publish memoirs describing the conditions they endured and identifying von Braun as one of the SS officers who visited the camp and selected prisoners for work details, and as historians who examine the documentary record demonstrate beyond reasonable doubt that von Braun and other paperclip scientists were directly complicit in war crimes, and that the sanitization of their records was a deliberate deception that allowed war criminals to escape justice and to enjoy comfortable lives and celebrated careers in America. Von Braun dies in 1977 before this ethical reckoning reaches full intensity, and he goes to his grave maintaining the sanitized version of his history and never publicly acknowledging his direct responsibility for the slave labor system that killed thousands of people in service of his rocket development work. The moral questions raised by Operation Paperclip and by American embrace of Nazi scientists remain contentious decades after the events because they involve fundamental tensions between competing values: the value of technical expertise and the contributions that German scientists made to American aerospace capabilities versus the value of justice for war crimes, and the principle that participation in mass murder should disqualify someone from honored positions regardless of their technical skills. The value of winning the Cold War competition with the Soviet Union versus the value of maintaining moral consistency in American dealings with individuals who committed atrocities, and the value of achieving the inspiring goal of landing humans on the moon versus the value of honestly acknowledging that the rocket technology that made this achievement possible was developed through means that included working prisoners to death in concentration camps. The survivors of dora-mittelbau and their advocates argue that von Braun and other paperclip scientists should have been prosecuted as war criminals rather than being brought to America, that their technical expertise doesn't justify allowing them to escape accountability for mass murder, and that honoring them as heroes of the space program represents a profound moral failure that prioritizes technical achievement over human dignity and justice. The defenders of Operation Paperclip and of von Braun's recruitment argue that the Cold War context made acquiring German expertise a strategic necessity, that prosecuting German scientists would have handed their knowledge to the Soviets, who were actively recruiting their own German experts, that von Braun's contributions to American aerospace capabilities, including the Saturn V rocket that enabled the moon landing, represent genuine achievements that benefit humanity, and that while his involvement in the slave labor system was reprehensible, his technical work created knowledge that has positive applications beyond the military weapons that initially motivated it. The technical legacy of the V-2 is unambiguous. Every large rocket developed after 1945 builds on technologies that the V-2 pioneered, including liquid-fueled engines with turbopump-fed propellant systems, regenerative cooling of combustion chambers, inertial guidance using gyroscopes and analog computers, aerodynamic configurations optimized for supersonic flight, and systems integration approaches that manage the complex interactions between propulsion, guidance, structures, and control systems. American rockets from Redstone through Jupiter through Saturn, I through Saturn V represent a direct lineage from the V-2, with each generation incorporating more powerful engines, more sophisticated guidance, better reliability, and enhanced performance, but all building on the fundamental architecture that von Braun's team developed at Peenemünde. Soviet rockets follow a parallel path from the R-1 V-2 copy through the R-7 ICBM, through Vostok and Soyuz spacecraft launchers, through modern Soyuz variants, and again the entire developmental progression builds on V-2 technology and on knowledge that Soviet engineers extracted from captured German hardware and scientists. The intercontinental ballistic missiles that define strategic nuclear deterrence throughout the Cold War and into the present are all descendants of the V-2, with American Minuteman missiles and Soviet SS-18 missiles and their successors using liquid or solid propellants, but employing guidance and control concepts that trace directly to V-2 innovations, and the terrifying reality of mutual assured destruction that shapes Cold War geopolitics and that continues to influence international relations, today rests on rocket technology whose genealogy runs through Peenemünde and dora-mittelbau. The space programs that inspire humanity and that expand our scientific understanding of the universe, that placed satellites in orbit providing communications and Earth observation and GPS navigation that modern civilization depends upon, that send probes to explore planets and moons and asteroids throughout the solar system, and that have landed humans on the moon and may eventually enable human settlement of other worlds, all built on rocket technology, whose development involved mass murder of concentration camp prisoners. And this connection between humanity's highest aspirations and its darkest crimes creates moral complexity that defies simple resolution. The city of Huntsville, Alabama, where von Braun worked for decades and where his team developed the Saturn V, has struggled with how to memorialize his legacy. Because while von Braun is unquestionably the father of Huntsville's aerospace industry and the person most responsible for the city's transformation from a small southern town into a major center of rocket development and space technology, he is also an unrepentant Nazi whose direct participation in war crimes makes celebrating him deeply problematic. The U.S. Space and Rocket Center in Huntsville includes extensive exhibits about von Braun and the Saturn V, and for decades these exhibits presented von Braun as a heroic figure with minimal mention of his Nazi past, but more recent revisions to the exhibits have attempted to provide more context about Operation Paperclip and about the moral compromises involved in bringing Nazi scientists to America. Though survivor advocates argue that even these revised exhibits don't adequately convey the horror of dora-mittelbau, or von Braun's direct responsibility for the deaths that occurred there. The question of whether it's possible to separate technical achievements from the moral character and criminal actions of the people who made those achievements remains unresolved and perhaps unresolvable, because the question involves values that can't be objectively compared or reconciled. The V-2 rocket is simultaneously a remarkable technical achievement that represents human ingenuity and engineering excellence applied to solving extraordinarily difficult problems, and a weapon built through slave labor under conditions of deliberate mass murder that killed more people in its production than in its use as a weapon. Von Braun is simultaneously a visionary engineer whose technical leadership enabled humans to reach the moon and thereby achieve one of the most inspiring accomplishments in history, and a war criminal who personally participated in a slave labor system that worked thousands of concentration camp prisoners to death and who never acknowledged his crimes or expressed genuine remorse for his actions beyond carefully crafted public relations statements designed to minimize his culpability. The American engineers who examined captured V-2 rockets in 1945 and who realized that German rocket technology was a decade ahead of American capabilities were confronted with a technical reality that demanded response, because allowing the Soviet Union to monopolize German rocket expertise while America tried to develop equivalent capabilities independently would have created strategic disadvantages that Cold War competition made unacceptable. The decision to bring von Braun and his team to America through Operation Paperclip was made on strategic grounds with moral considerations subordinated to geopolitical calculation. And while this decision can be understood and perhaps justified in the context of the emerging Cold War, it created moral debts and contradictions that persist decades later, because the decision involved embracing war criminals, concealing their crimes through deliberate falsification of records, allowing them to escape justice and to enjoy celebrated careers, and teaching the lesson that technical expertise can excuse even participation in mass murder if the expertise is valuable enough to powerful interests. The technical examination of the V-2 that American engineers conducted revealed not just the rocket's capabilities, but also the reality that achieving major technical advances requires enormous resources, specialized expertise, and often years of sustained effort, and that there are no shortcuts to developing complex technologies like large rockets. The knowledge that American engineers gained from studying V-2 hardware accelerated American rocket development by providing solutions to problems that American engineers would otherwise have had to solve through trial and error. And this acceleration meant that American missiles and space launch vehicles reached operational capability years earlier than would been possible without access to German expertise and hardware. Whether this acceleration justified the moral compromises involved in Operation Paperclip remains a question that people of good faith can disagree about, because the question ultimately asks whether technical progress and strategic advantage justify collaboration with war criminals, and different people weighting different values will reach different conclusions. The V-2 program's economic irrationality is clear in retrospect. The Germans spent resources equivalent to the Manhattan Project on developing and producing a weapon that had minimal military effectiveness, that killed fewer people than the same resources invested in conventional weapons would have killed, and that diverted industrial capacity and skilled labor from production of tanks and aircraft that might have been more militarily valuable. Albert Speer, Hitler's Minister of Armaments, later wrote that the V-2 program was a mistake that consumed resources needed for conventional weapons, and that the rockets' poor accuracy and high cost meant they never could be militarily effective. And Speer's assessment is confirmed by analysis, showing that the same resources invested in fighter aircraft would have shot down more Allied bombers and caused more Allied casualties than the V-2 achieved. But Hitler insisted on wonder weapons that he believed would somehow reverse Germany's military situation through technological surprise, and the V-2 program continued consuming resources until Germany's collapse, despite rational analysis showing it was wasteful. The irony that more people died building V-2 rockets than were killed by V-2 strikes crystallizes the program's moral bankruptcy, because it demonstrates that the weapon was literally more deadly to the people forced to produce it than to its intended targets. And this inversion of normal military logic, where weapons are supposed to harm enemies rather than the people building them, reveals the extent to which the Nazi system had become fundamentally irrational and destructive even to its own interests. The prisoners who died at Dora-Mittelbau were overwhelmingly political prisoners, Jews, Soviet prisoners of war, and other people whom the Nazis categorized as enemies or as racially inferior and therefore expendable. And their deaths served no military purpose and achieved no strategic objective beyond satisfying the Nazi compulsion to extract maximum suffering from people they had categorized as subhuman. The technical sophistication of the V-2 makes the program's moral horror more rather than less disturbing, because it demonstrates that technical brilliance and engineering excellence can be employed in service of evil, that the same human capabilities that enable inspiring achievements like space exploration can also enable industrialized mass murder, and that there is no inherent connection between technical skill and moral wisdom. Von Braun possessed genuine genius in rocket engineering. He solved extraordinarily difficult technical problems through innovative approaches that advanced human knowledge, and his work enabled achievements that inspire and benefit humanity. But these technical accomplishments coexist with his willingness to participate in mass murder when such participation served his goal of building large rockets. And this coexistence demonstrates that technical capability and moral character are independent qualities that can be present or absent in any combination. The space age that the V-2 enabled has brought enormous benefits to humanity through communication satellites that enable global connectivity, through Earth observation satellites that provide weather forecasting and environmental monitoring and disaster response, through GPS satellites that enable navigation and precise timing that countless modern technologies depend upon, through scientific satellites that have revolutionized our understanding of the universe and our planet, and through the inspiring achievement of human spaceflight that expands our conception of what humans can accomplish and that may eventually enable human settlement beyond Earth. These benefits are real and valuable, and they justify the continued investment in space technology and in the rocket systems that enable access to space. But acknowledging these benefits doesn't erase the crimes that were committed in developing the foundational technology, and celebrating the achievements while ignoring the atrocities represents a moral evasion that fails to grapple with the full complexity of the historical record. The American engineers who examined captured V-2 rockets in 1945 were confronted with technical sophistication that exceeded their expectations and that forced them to acknowledge that German rocket engineering had achieved capabilities that America lacked, and this realization drove American decisions about recruiting German scientists, about investing in rocket development programs, and about competing with the Soviet Union in the emerging missile and space races. The examination revealed not just what the V-2 could do, but also how it worked, and this knowledge transfer accelerated American rocket development in ways that shaped the entire subsequent history of aerospace technology. Whether the knowledge was worth the moral price of embracing the scientists who developed it through slave labor remains a question that each person must answer according to their own values and their own assessment of how to weigh technical progress against justice and moral consistency.